Guten Tag, Saubona, and good day to our fellow WAP colleagues. My name is Sarika Devraj, and I am from eThekwini Water and Sanitation from sunny Durban. Our WAP entails the development of a low-cost smart water metering device to develop a smart grid to curb non-revenue water losses within the city of eThekwini. In a global context, eThekwini is located in a subtropical climate on the southern tip of South Africa. The city is on the east coast of South Africa and is home to approximately 4 million citizens, which makes it the third most populous city in the country. eThekwini has a high topography with a very hilly landscape, which ultimately impacts on the water and sanitation infrastructure. The city experiences high poverty levels and with a high unemployment rate of 33.9%. eThekwini is a water scarce city that imports around 90% of its water. There are 1.1 million households within the city, 65% of which is deemed as indigent, the highest indigent rate of any city within the country, with second highest city having 45%. The city purchases around 1 billion liters of water a day, 500 million of which is unaccounted for, thus resulting in non-revenue water in excess of 50%. The city has high levels of non-payment, which further weakens the city's economic stability. Some of the challenges faced by the city include high non-revenue water, as already mentioned, high indigent population of 65%, a high volume of informal settlements, and a rapid influx into the city. This has resulted in a high percentage of indigent households to paying households. eThekwini has 12,500 kilometers of water networks and around 270 reservoirs that covers the entire city. There are 500,000 metered connections. However, the city is plagued with aging infrastructure. Ngeni Water, who is the bulk water supplier, has reached the limit of their license capacity as well as the limit of physical capacity. Current average daily demand for the city is around 1,000 million liters a day. Growing demand and urbanization is outstripping the supply. There is a need to reduce the consumption and improve efficiency is becoming a priority for the city. The diagram displays the reservoir hierarchy of a custody transfer point or point of bulk water purchases. We have 70 custody transfer points that feed level 1 bulk supply reservoir, which then cascades to level 4. A reservoir can supply a lower level reservoir or the consumer directly. There are critical areas of the network that require the smart metering to enable a smart grid. This is a complex diagram which illustrates one part of the network. It is the most important to note that we have installed around 3,000 pressure reducing valves to help reduce non revenue water. This helps to reduce the amount of water lost through leakages or burst, ultimately reducing the strain on the system. The benefit the benefit to this project is that one of the pressure reducing valves of these pressure reducing valves, a flow meter can be attached to it. When installing the smart grid devices to the flow meter on the pressure reducing valve, we can produce a smart grid. This will highlight the areas of high losses, help us to get zonal balances, provide an early warning system for leaks and burst, provide usage patterns for each area, allowing us to harness artificial intelligence and machine learning. One of the quickest wins is that we will be able to read night flows on individual meters, which can directly point to major leaks and bursts. These images are examples of a typical bulk meter at a point of purchase. The benefits of smart metering will be quick response to repair teams, capture inherent knowledge and skill, create dashboards and use predictive technologies, incorporate artificial intelligence and machine learning. There are 500,000 existing domestic meters in the city. The cost of a smart meter is roughly 150 USDs, each which calculates to 75 million USDs to cover all existing meters. The cost implication makes this project not feasible to be undertaken in the city. This excludes the cost of resources required for plumbers and to refit meters. In order to address these issues, a hackathon was held at the Botanic Gardens in August 2022 in Durban. The iterative design thinking approach was used to get all the role players to understand the magnitude of the problem. Because the solution did not only lie with the water experts, professionals from the IT and electronics fields were also included. We included civil society, councillors, and senior managers from the city who were there to articulate the need to resolve the high non revenue water. We looked into consideration when designing the solution, the device, power supply, and data conveyance tampering. Do we use the existing device or replace it with an all new electronic device? There are many where m- there may be trust issues with the new device, whereas the consumer is already confident with the already existing device, for which has approval for installation within the city. Cost will be higher in terms of installation if you need a plumber to replace the device. With existing devices, you can get a pulse using the read switch or take a picture of the already existing readings and use artificial intelligence to be converted to the number. Then you can also get the readings digitized. The many options for powering device include rechargeable batteries, which are quite expensive and require replacement over time, solar, which presents the risk of theft of the solar panel, hydroturbine, which uses the existing flow in the pipe to provide power, mains power from the residence itself, wind, or any combination data conveyance. We could use our refuse trucks, which traverse every road in the city at least twice a week, to gather this data and then read it into our system. There are many IoT devices using GSM cellular network. This is very efficient way to get the data. In addition to the cost, a SIM needs to be installed into the device. This means that when we change service providers, we will have access to each of the 500,000 devices to change the SIM. Sigfox is extensively used in South Africa for vehicle tracking and has a coverage throughout the city. Each device requires a license, and that cost is out of our control, which means that again we would have to access each device if the cost of Sigfox becomes too high. Also, Sigfox is one way uh, communication. So if we decide to control a valve on the meter remotely, we would not be able to. LoRa is a free low band network coverage that has partial coverage through the city. The cost of installing transmitters for the rest of the city uh, could could be phased in affordably. The city could eventually own its own LoRa network. The city has extensive fiber coverage, which poses an opportunity for high-speed data. That investigations into the device are ongoing. The city also has its own radio network, which it's with its own radio towers that requires conveyance data. But it's not a feasible option for us because the device costs for accessing the radio network are exorbitant. Tampering could also happen for many reasons, chiefly if there is value in the device or if the readings are being measured are to be obscured in favor of the homeowner. Creating value to the customer may lead to him taking personal accountability for the device and ensuring its safety. Accurate readings from the houses can serve as a credit report for borrowing money. It is also an early warning tamper proof, which can also be built into the device where it becomes useless or sounds an alarm once tampered with. The materials should also be low value. One of the interesting things that we can do with having a smart metering device at the household level is to gamify the use. So, lowest per capita use on a street gets recognition or rewarded. This can drive water conservation. There are many opportunities to gamify. The results of the hackathon produced a workable device using available technology. a device using an ESP32 AI camera chip, which will take a picture of the existing meter and convert it to numbers. The data is conveyed back to the system. We are currently building 100 devices using off the shelf equipment to prove the concept. These devices will then be installed at various points in the system to test the suitability and functionality. Thereafter, we plan to create a specification for the fabrication. Thank you and Sia Bonga.